All right. Now that we have learned the different gas laws, no, the individual gas laws crafted by different scientists, as well as the combined gas law, we now go to the final equation. No? And I think this is one of the most elegant equation in the universe. The ideal gas equation. So why do I say it's one of the most elegant equation? Because probably after several years of study, after several years of experiments and arguing and debate, no, they've been trying to create one equation to explain how gases behaves. So let's just recall how really gases behave. Say for instance, I have a balloon here. So I have a balloon. Yeah, don't think of anything else. That's a balloon. Inside a balloon, there are gases, no? And we know that gases are moving around. They are moving at random motion, either hitting the wall of the container and bumping into each other. That's their specific motions. So we can say that here there's a temperature. Now we have a temperature here, and we use Kelvin as a unit for our temperature. So if we increase the temperature of this balloon, the gases will move faster. There will be more excited and the kinetic energy would rise. No? You've learned that in the kinetic molecular theory, the behavior of gases. Also, inside the balloon, we have the pressure. So we have pressure inside the balloon. So the pressure is in ATM. So that is our unit for our pressure. Say for instance, it's 1 ATM, etc., etc. And then we also learned that that balloon, particular balloon, has a specific volume which is in liters. And then eventually, there's an amount of gas, or how much gas is inside that particular balloon. And that is your N. So we have the four specific values or four specific factors that has already been discussed, no, and has been already correlated by different scientists. Now, the goal again of science is to create one unique equation for all the different equations, no, to combine them to create a theory for everything, a single equation that would explain everything. Now, interestingly, in the Avogadro's law, now if you can remember, maybe we can again have a recall because these are a lot to take in. But I will no longer indicate or write rather the names. So I'll just mention it. So for the Boyle's law, we have the relationship of the pressure and the volume, which is inversely proportional. So this is your Boyle's law. So maybe I can abbreviate na lang BL. Charles's law, I have VT T2. Gay-Lussac's law, GLL. That's P1 T1 is equals to P2 T2. And then maybe I can write the combined gas law as CGL, combined gas law. That is your PVT is equals to PVT 2. And then the Avogadro's law as V1 N1 is equals to V2 N2. Now these are a lot of equation. Now this equation that we hate to memorize. What if I can say to you that we can combine them all, no, so that we don't need any kind of memorization? So how do we do it? The question is, again, scientists have thought the combined gas law was the absolute law, no, or the final equation. And here comes Avogadro saying maybe we can input the number of moles in our equation. Now, where do I put this N, no, in the equation so that it would not violate any of the laws that has been crafted several years before. So the only option is to check where the volume is located. So the volume is always in the numerator. So meaning I don't have to change my volume. Pressure, it's always in the numerator. So meaning the pressure is there. And the temperature is always in the denominator. Now, hopefully you can follow. So therefore, I just need to put my N where? Very good. In the denominator. I should put my N in the denominator. So that would be P1V1. This is the combined gas law. P2V2 N2. That's the combined gas law. T2 rather. T2. Sorry. Yeah. T2. And I have to place my N1 and then my N2 here. So does it violate any of the law? Let's check. If I cover the denominator, that is my, very good, Boyle's law. If I cover my, say for instance, pressure and N, that is my Charles law. Very good. If I cover this two, that is my, very good, Gay-Lussac's law. If I cover pressure and temperature, yan, that is my Avogadro's law. If I cover my N, that is my, what? Combined gas law. Very good. Right? Amazing, wonderful, extravagant, elegant. But that's not it, that's not all. There's something more interesting Avogadro had discovered in this particular scenario. So, if you can notice, in these equations, diba, we've kept on writing it in a constant form, like in a proportionality, in a relationship form. Say for instance, the pressure and volume, right? The electric fan is making things difficult. Okay, thank you. And pressure is 1 over volume, like that. They're inversely proportional. So sometimes it's written like that one. Volume and temperature would be like this one. Or we simply say that P V is equals to a constant. So here, what is the constant for this particular equation? Let me rewrite this one, the combined gas law. So pangit naman kung sabihin na combined gas law 'yon. So the combined gas law again is P1V1 T1 is equals to P2V2 T2, and I added the number of moles, so N1 N2. So this is now your combined gas law, but that's not the name yet, but we combined the Avogadro and the combined gas law, so I simply call it combined gas law. Now, if I have to rewrite it in a single equation, PV NT is equals to a constant, a random constant, anything, as long as we follow the specific units, the correct terms, etc., etc. But Avogadro realized something, at a standard temperature and pressure, so bear with me, at STP, maybe you're familiar with this one, meaning standard temperature and pressure, the standard temperature is 0 degrees Celsius, which eventually is 273 Kelvin because that's our unit. Our pressure is 1.0 atm. Avogadro realized that at this standard temperature and pressure, which is 273 Kelvin and 1 atm, any mole of gas, meaning 1.0 mole of any gas, will have a volume of 22.4 liters. Very, very amazing because he tried several gases. He tried computing and experimenting with different gases. 1 mole of helium, 1 mole of oxygen, 1 mole of argon, no, at 1 atm and 273 Kelvin, and it always ends up with 22.4 liters. And when we input that in our calculator using this equation, so our P is 1.0 atm, my volume is 22.4 liters, my N is 1.0 mole, and then my T is 273 Kelvin. What are we going to get? Now, what would be our K? So, let's place that into calculator. 1.0. Of course, this is just 22.4 over 273. So, you'll follow 22.4 divided by 273. That would give me 0.820, or simply 0.821. That would give me electric pan 0.821, and the unit